Alright, let's check out 3 more examples. This one is, we're just going to solve this like normal. When we square root both sides, you have to remember the plus and minus. So, just like anything else, we're going to add 1, divide by 3. And I think that much you already knew. Now this is what I was just talking about. Once we get to this point, tan squared x equals 1/3. We do have to square root both sides to get tangent x and what it is equal to. When you do that, because we are square rooting both sides of an equation, you have to remember the plus and minus sign. So we go like this, and we have tangent of x is equal to plus or minus 1 over the square root of 3. And that is not rationalized, so you might actually recognize this more as the square root of 3 over 3 on your unit circle. So, these are our solutions, plus and minus the square root of 3 over 3. We are looking for 2 solutions here because we have a plus and minus. So, the period of tangent is pi. So, we're going to look at all the solutions in that interval, in just the interval of pi. Once we find those solutions, then we can move on to find solutions outside of that interval. So, find solutions in 0 to pi. And those solutions, look at your unit circle, set up a triangle, however you do it. Those solutions in 0 to pi are going to be x equals pi over 6 and 5 pi over 6. But these are only the solutions in this range, in this interval. So if we want to consider the solutions in all solutions, so we have to go back and realize that tangent of theta has a period of pi. So we're going to add and subtract pi. So our final solutions are going to be x equals pi over 6, and just like the other day, plus pi n and 5 pi over 6 plus pi and n, where n is an integer. So this is our actual solution here. These are the solutions just in this range, just in the first period. But if we want to look at all of the solutions here, we have to add and subtract the period of pi repeatedly, infinitely, to get every solution. So this notation represents every possible solution of this function. All right. So, just so you know, when you're doing these, if you have anything that is sine, cosine, secant, cosecant, the period is 2 pi. So you would do 2 pi n on each of these. But for tangent and cotangent, because the period is only pi, we're just going to add and subtract the pi n. And when I subtract, I mean if n is negative, then this would become a subtraction, or adding a negative. Alright, so we're going to continue solving, and the next one we're going to solve, we're going to do so by factoring. So, let's start that. Cotangent x cosine squared x equals 2 cotangent x. Alright, so first thing is, if you see multiple terms, you see a squared, you see 2 different expressions, typically you want to pull everything to one side. So the equations that we solved for the most part so far have all been a single trig function, just one of the 6, and we either combined them, we were able to pull them all over to one side. This is a little bit different. We have cotangent and cosine, and we have them on both sides. So let's pull them to one side and see what we can do. Cotangent x cosine squared x minus 2 cotangent x equals 0. So we pushed that to the other side. It became negative. Now, what we can do here is factor. That's pretty much our only option. We can't combine these because this one's squared and these are something completely different, cotangent versus cosine. So our only option is to factor and see what we can do at that point. I'm going to factor out cotangent x, leaving behind cosine squared x from the first term and just a 2 from the second term, and that's going to equal 0. Now we can apply the zero product property and separate these. Cotangent x equals 0, and cosine squared x minus 2 equals 0. So this one we can actually solve. So once again, however you figure this out, looking at your unit circle, cotangent x equals 0. That gives us a solution of x equals pi over 2. Right? So next we have cosine squared x minus 2 equals 0. Anyhow, I'm going to add the 2 over. Cosine squared x equals 2. Square root both sides. Don't forget about the plus and minus, so cosine x is equal to plus minus square root 2. Now, this one's a little bit different. We have some extraneous solutions here because we know, if we go back to the last video, if we were to graph the cosine curve, it would bounce back and forth between 1 and negative 1. The square root of 2 is roughly 1.4. So this is roughly plus minus 1.4. So if we graph the cosine curve and then we graphed a horizontal line at 1.4, they would never intersect. This is not going to create any solutions. If you want to verify that, we could actually solve in another manner. You could actually say, if x equals the arc cosine of square root 2, if you were to type that in, you would get an error because it is outside of the range. So either way, these are extraneous, well, they're not extraneous, it just, there are no solutions here. So we can actually kind of just ignore that, and this is our only solution. But once again, this is just a solution in that range, so we have to consider cotangent has a period of pi. So when we do our actual solutions for this, it's going to be pi over 2 plus pi n, where n is an integer. This is just the one solution in that period, and then this is considering every possible solution of this. Okay. So I have one more for you, and this is still factoring. It's factoring in a little bit of a different style, but nothing that you're not already used to. So let's try this one out. What if we have 2 sine squared x minus sine x minus 1 equals 0? So this can actually be factored in the same exact manner as any sort of quadratic, because it's sine squared, a plain sine, and then no sine. So just like if you had 2a squared minus a minus 1 equals 0. If you were being asked to factor this, this can be done the exact same way. And if you want to, you can actually rewrite these and then use the pattern and kind of use that to end up helping you factor this. So if we were to factor this, 2a and a, we need to get a negative 1 in the middle. So I'm going to do this, because what I'm going to get here, and the way I can double check this, I can simply factor it out, or excuse me, FOIL it out. So 2a times a is 2a squared. 2a times negative 1 is minus 2a plus a minus 1. And when I combine these, I'm going to get a negative a. So I can see that this matches back up to that. I always recommend multiplying this back out quickly just to double check. Anyhow, I see now how this will factor. I can go back over here and factor this into 2 sine x plus 1 in the first parentheses and sine x minus 1, just like that. And this step is not necessary. If you're able to do that without that step, then by all means, don't do that step. Anyhow, same thing as up above, zero product property, separate these. 2 sine x plus 1 equals 0, and sine x minus 1 equals 0. When I solve this, 2 sine x equals -1, and sine x equals -1/2. So, in the period from 0 to 2 pi, the solutions of this will be x equals 7 pi over 6 and 11 pi over 6. Over here, add the 1 over to the other side. Sine x equals 1. So when is sine x equal to 1? That is at pi over 2. And once again, that's on the interval from 0 to 2 pi. So these are the solutions in that interval, but we want all the solutions on the entire number line, so we have to write them just like we did before. All right, so x equals 7 pi over 6 plus 2 pi n. Once again, we're using 2 pi because this is a sine function, comma, 11 pi over 6 plus 2 pi n, and pi over 2 plus 2 pi n. Those are your three solutions, once again, where n is an integer. All right. The questions I'd like you to try that are kind of in this same realm, on page 376, I have 3 of them for you today. Try out 15, 21, 25, and 29. And submit them when you finish them. If you have any questions or want to go through one of them, just send me a message and we can do that.